Um, I'm sorry for the delay, and this is a delay of a delay. But a couple of things. One, I got your quizzes up. Um, Milo was uh, one of your classmates, Milo, added to a discussion, the discussion board on Canvas, some hints and suggestions and some tips for how to make sure that Proctorio works. And I mean, it's pretty simple and straightforward. It's like 3 steps. One of the things is you've got to use Google Chrome as your web browser. So make sure you get that set up. Then so there's a Proctorio quiz that's open. And what I want you to do is make sure that that works for you so that you can actually take the quiz. And then so you can actually take the exam. Sort out any Proctorio related issues now rather than on exam day. Now, with that in mind, um, the the biggest thing with respect to Proctorio, or the most common email that I get about Proctorio, is people saying, "Oh, I didn't get the access code," or "Hey, what's the access code?" And the access code is dictated or managed by Proctorio. So if you are prompted when you're trying to take that Canvas quiz for an access code, that means that Proctorio isn't active or is inactive. Maybe that's because you have a pop-up blocker or you're just not somehow using the wrong browser or something like that. But make sure that you um, take that into account. If the browser, or if you try a different browser and you still get that issue, then try a different computer. And if none of that works, I would contact ITAC, ITAC at txstate.edu, ITAC at txstate.edu, and or 512-245-4822. Okay, I'm guessing that they'll probably go through the same sequence of suggestions that I just posed to you, but nevertheless, that's the biggest issue. Typically, whenever you implement that, then the issue resolves itself. Okay, so next up is thanks for looking. Oh, so I also posted, this is the other thing that I'm apologizing for taking so long, is I posted the learning objectives for this first bit of material for your first exam. Um, so the learning objectives are basically what I did to kind of compile them was went through our PowerPoints. And there are some things that I did not include, but that's not like an intentional omission of like, this is not going to be on there at all. However, the way that I'm going to write my exam is I'm going to take those learning objectives that I shared with you, and I'm going to look at the PowerPoints and I'm going to be like, okay, there's a point about um, equilibrium, shifting to the right or to the left, KEQ values. Um, that's that's how I'm going to write the exam. I'm going to share before the end of this week some of my old exams. The one thing that I want you to be cautious of when you look at those old exams is that they might not align directly with um, the content on this first exam, and that's because we've added glycolysis to what we cover on this in this class. So I'll be posting those before the end of the week, and I'm going to go ahead and just post exams 1 through 4, or old exams 1 through 4 for that. Now, then I got some other questions. Which quiz of the two do we take? There's one due tomorrow night on Canvas, and then the proctored one is due Monday night. They are 2 separate quizzes. Take both of them. The Proctorio quiz is intended to be like the simplest answer ever, or simplest question ever. It's 10 points, essentially freebie points. The other quiz is over content that we've covered. Now you have 2 attempts at the quiz with the content that we've covered, and this is an open note item. So go ahead and take those 2 attempts. You'll get the score of that first attempt, but you won't be told which questions you got right or wrong. So that's where you kind of have to take that second opportunity to take it, or use your second attempt. Next question. I had some confusion over the method of proctoring. The test, this says I'm sorry. I'm sorry. It is Proctorio. That is the way that we are taking our exams because this is a 100% online class. I'm sorry for the confusion. I'll fix that on the syllabus today. What type of question should we be looking for? Open answer or multiple choice for the test? Most of your questions on the exam are going to be multiple choice or multiple answer. So multiple answer question would be something like, select all of the following true statements, or select the statements from those below that are true. Or for an example, which of the following sugars are aldoses? And then I'll give you the names of a handful of sugars and you'll have to determine which ones are the aldoses. Is there any specific content for we should review before the quiz? Not particularly, because it's an open note quiz. You have 15 minutes. I mean, I would just kind of run through my PowerPoints. But the quizzes are basically, I'm looking at the quizzes as equivalent to homework. It's homework with a time frame. That's all there is. That's the only difference. And you have 2 attempts. With the quizzes being open note, do they need to be paper copy or? So the quizzes are not going to, just a second. No, the quizzes are open documents. If you want to use PowerPoints, you can use PowerPoints while you're taking the quiz. The quizzes are not going to be administered by Proctorio. Only the exams are going to be administered by Proctorio. This one quiz is an exception to that rule. This one quiz is an exception, and it's really to make sure that whenever an exam comes around, you have all the systems in place to take that exam. So that's the only reason that this is an administered quiz by Proctorio. You can work on these quizzes in groups. It's really no different to me. Like I said, the quizzes are termed quizzes, but they're effectively like homework with a time limit. Okay, thanks. How many questions on the exam? I'm sure it was mentioned. The exams are typically going to be between 25 and 35 questions. The learning objectives seem straightforward. Are the exams also that straightforward? That's my plan. I'm not looking to like give you any sort of like decoy questions. There are some times whenever I ask a question that does require like a next level of understanding and thinking and processing of the information. But I'm not trying to ask questions that anyone would term as gotcha questions. Like, I want you to be able to identify amino acids. I've told you the sugars that I want you to know, the aldoses and ketoses, the specific structures. So I might give you a question that is, what is the name of this sugar? And then I might give you a question that is, here's a sugar. This sugar is a what of something else. So that what of something else would be something like, this sugar that you're seeing is a C3 epimer of glucose, for example. Yes, we will be using Top Hat, and that will account for 10% of your grade. We haven't used that yet, but like I've said previously, I'm going to make an announcement like, hey, we're having Top Hat today, or you should expect Top Hat over the next few lectures. Okay. Well, I hope that answers everyone's questions. I think that I went through. Yeah, I think that's all of them. So now I am going to switch over to share. Would the announcement be the day before or day of for Top Hat? Expect something like, hey, the next few days we're going to be using Top Hat. And so then I'm not going to send one out every day. But typically it's going to be prior to that class meeting. So like, the day before at very latest. I'm not going to spring it on you, like not say anything and then Friday, surprise, Top Hat. I don't think that's very pleasant for anyone. Okay, so here is the PowerPoint that we completed last time. And this was simply over glycolysis. And with respect to glycolysis, we were looking at the initial investment phase of glycolysis. Simply put, this was basically 3 steps. Our input was glucose and our output was fructose bis 1,6-bisphosphate. So we took an aldose, we phosphorylated it, we isomerized it to make a ketose, that being fructose 6-phosphate, and then we phosphorylated it again to make fructose 1,6-bisphosphate. Now that's the whole thing in a nutshell. That's the whole thing of the first part of glycolysis in a nutshell. Now, after that fructose 1,6-bisphosphate was produced, what we're going to do is we're going to go on and we're going to try to get back some of that ATP, because in these first three steps, we invested ATP. Now what we want to do is we want to get some of that back, because this metabolic process known as glycolysis, the entire kind of sales pitch of it almost is, hey, you get energy from this. How are you going to extract energy from glucose? So that's where we are right now with, the process of glycolysis, or the phase of glycolysis, kind of known as the return phase, and the return or the payoff phase. So the first enzyme that we see in glycolysis is simply known as aldolase. Now, aldolase is an enzyme. Oh, that's not what I wanted to do. Oh, that's not. There we go. Aldolase is an enzyme. And just so you guys know, we'll be looking at, I'll show you some mechanisms, but for the most part, moving forward, you're going to kind of hold on to your mechanisms until 4385. So aldolase is a metabolic, or it is an enzyme that's going to take fructose 1,6-bisphosphate, which here's fructose 1,6-bisphosphate in its linear form. What we've seen up until now is this structure right here. And I'm going to skip over drawing those hydroxyl groups, but effectively this is what we have. And what we want to do, and what this enzyme is going to do, is basically split it right down the middle. And by splitting it right down the middle, we're going to generate two products. One of them is glyceraldehyde 3-phosphate, and one of them is dihydroxyacetone phosphate. Now, when you think about the terms aldoses and ketoses, using these acronyms, GAP and DHAP, which one of these two is a ketose? Perfect. Dihydroxyacetone phosphate, DHAP. So to me, the most productive and helpful way to think about the products of glycolysis, and I use these terms products and intermediates, I'll use those sometimes interchangeably, because DHAP and GAP are products of aldolase, but it's also the substrate for the next enzyme. So that's why some folks will refer to this as an intermediate of glycolysis. It's a product, or these two molecules right here are products of aldolase, but they're intermediates in glycolysis. So I don't want you to get hung up on those terms and those differences, those distinctions, but I do want you to be kind of thoughtful of them. So DHAP is a ketose, and glyceraldehyde 3-phosphate is an aldose. Now, one of the questions that I gave my students a few years ago was, we had been talking about glycolysis, and then I said, draw glyceraldehyde 3-phosphate. Okay, so they came up with this. But then I said, at a later date, I said, draw glyceraldehyde. And there were lots of folks who were just they were confused. They didn't know how to answer that question. And to me, that was a little bit of an indication. And I say this from my own personal experience, because my professor did the same thing to my class. I had committed this structure to like muscle memory. I could draw that 100 times, no problem. And it was just like not thinking. But then when they said draw glyceraldehyde, then all of a sudden I was like, oh, rats, I don't know what any of this means. Because I had almost like neglected to think about, well, this part of the molecule, 3-phosphate. That tells me information about this molecule. This is carbon 1, 2, and 3. So all that I was really looking for with that question was to draw this right here. And I bring this up as kind of a cautionary tale and as a, be thoughtful, be thinking about what you're drawing, which is one of the reasons that I always like to say what aldolase does is it takes a ketose, a doubly phosphorylated ketose, and it makes an aldose, and then it makes a ketose. It splits it right down the middle. That makes it, to me, much easier to remember these different structures and remember the similarities, but remember the differences between them. So that's what we're getting whenever we run the aldolase reaction. Now, it is valuable to kind of be thoughtful of and remember where the different carbons come from. So we've got these little symbols, this star and then this kind of double S structure there to indicate which carbon we're talking about. If you remember, it's fructose 1,6-bisphosphate. So on carbon number 1, there's a phosphate, and on carbon number 6, there's a phosphate. Now, this part of our molecule and this part of our molecule are going to be different from one another. This is going to make, or the top half of your molecule is going to make your dihydroxyacetone phosphate. Your bottom half of your molecule is going to make your glyceraldehyde 3-phosphate. The star, so basically carbon number 6 becomes carbon number 3. And then carbon number 1 becomes carbon number 1. Now, this is a reaction that's taking place through covalent catalysis. This I'm going to leave here. We haven't talked about catalysis, but I'm going to leave this here so we can revisit it and later on when we talk about enzyme catalysis. And this is something that will be valuable when you take 4385, should you take that. If you're not going to take that, then don't worry about this. But essentially, in order for this reaction to take place, a covalent bond has to be made or broken, or it has to be made in the mechanism of this reaction. We'll talk about covalent catalysis later on, but covalent catalysis is a type of catalysis where a covalent bond between enzyme and substrate is formed. And here's exactly where that's taking place. We've got a pair of amino acids, lysine and aspartate, that are going to participate in that covalent catalysis. Now, for this, don't worry about all of this reaction. But what I do want you to know is that lysine and aspartate are 2 amino acids that are participating. We're going to get into amino acids after this first exam. So this is exam 2 stuff, looking forward a little bit. But I want this to be something that you're thoughtful of, that amino acids are not simply a dietary supplement or something that, yeah, they build up proteins. Sure, they do build up proteins. All amino acids that build up proteins have different reactivities and different functionalities. And 2 examples are these 2 amino acids that participate in enzyme catalysis and catalyzing a specific or catalyzing reactions. Now, aldolase, the reaction or the enzyme, is reversible despite a high delta G naught prime. So what that means is that when we think about our reaction steps that are irreversible, we have our first reaction catalyzed by hexokinase, our third reaction catalyzed by phosphofructokinase, and then our last reaction catalyzed by pyruvate kinase. So aldolase, it seems almost as if, well, it shouldn't be reversible. It is. We have this molecule that's being broken from 6 carbons down into 2 3-carbon molecules. Well, that reaction can go back just as kind of easily. It is a reversible reaction. Now, here's kind of the progression of our molecules. Acetone, dihydroxyacetone, where we have two hydroxyl groups on our carbons 1 and 3, and then dihydroxyacetone phosphate, where one of those hydroxyl groups has simply been replaced by a phosphate. So these hydroxyl groups, and this is something that you'll notice when we talk about proteins and when we talk about sugars, these different hydroxyl groups, or sorry, hydroxyl groups in general, are ripe for being replaced by a phosphate. It's very common that that will happen. And that's just because these hydroxide groups are good leaving groups for, they're good leaving groups in general. Now, what we have to do next, when we come out with, we come out with these two different molecules, or actually here, let me pause. Does anyone have any questions about aldolase and the products of aldolase? I'm going to drink some coffee while. Okay, great. So we've generated, like I said previously, an aldose and a ketose. Summer, that's a great question. There's actually only two. These three molecules, this is just showing, so this is one of our products of aldolase. Our other product is glyceraldehyde 3-phosphate. So these three different structures, what I'm really trying to share with you and help you understand is the nomenclature behind dihydroxyacetone phosphate. So acetone is 3 carbons. It's a ketone. It's almost, well, it's a 3-carbon ketone. We have 2 methyl groups and then a carbonyl carbon. Dihydroxyacetone. Well, if you use acetone and you put 1, then 2 hydroxy groups, you have dihydroxyacetone. Then this last one, you take the structure of acetone or dihydroxyacetone, and you replace one of those hydroxide groups with a phosphate group. That's really just how we get to dihydroxyacetone phosphate nomenclature-wise. So now, just to bring back to what are our products. So these two products, glyceraldehyde 3-phosphate and dihydroxyacetone phosphate, are the two products from aldolase. So aldolase, I'm going to write F16BP generates that and that. Okay, so those are our two products. But when you think about this metabolic pathway known as glycolysis, we end with one product. We end with pyruvate. So what we need to do is take these two different products, this ketose and this aldose, and generate only one product from this. And so then essentially the question is, how do we proceed through glycolysis? And I want to share, I'm going to switch my share for a second to this right here. If you look at this right here, got draw. We are right here. Okay, so we make GAP and DHAP. What we need to do is we need to replace that dihydroxyacetone phosphate with glyceraldehyde 3-phosphate. So what we need to do is we need to isomerize dihydroxyacetone phosphate into glyceraldehyde 3-phosphate. The question is, why is it still dihydroxy if one of them has been replaced? I think that ultimately goes back to the dephosphorylation that molecule can undergo. Um, I think, yeah, that would be my best answer. So what we need to do is we need to get dihydroxyacetone phosphate converted to glyceraldehyde 3-phosphate. And that's exactly what the next enzyme in this pathway is going to do. That next enzyme has a pretty simple name. That pretty simple name is, I'm going to start at the end. It's an isomerase, and it acts on two different trioses and a phosphorylated triose. So triose phosphate isomerase. This enzyme will take our ketose, our dihydroxyacetone phosphate, and convert it to glyceraldehyde 3-phosphate, which is what we want, because glyceraldehyde 3-phosphate will be able to continue and progress through our pathway. So when we do this, we've basically just rearranged. We've gone from a ketose to an aldose. And I always like to think about this because then I can say something like, okay, fructose 1,6-bisphosphate uses aldolase, and it comes up with an aldose and a ketose. The aldose that we produce, the glyceraldehyde 3-phosphate, can go through glycolysis. The ketose, on the other hand, well, the ketose does not proceed through glycolysis. It has to be converted to the aldose. The aldose, glyceraldehyde 3-phosphate, can then go through glycolysis. So triose phosphate isomerase catalyzes that reaction. So now we are right here, where we have two molecules of glyceraldehyde 3-phosphate. That's a reversible reaction. So we now are working with two identical molecules. So everything that we do from here on is going to be shown one reaction, but it's going to take place twice because we have two 3-carbon molecules. Now, with respect to products that are generated from this isomerization, there's no like ATP or NADH or anything like that that's produced here. It's just two molecules of glyceraldehyde 3-phosphate. So now what we're able to do, when we get to this glyceraldehyde 3-phosphate, the two glyceraldehyde 3-phosphate molecules, now we're kind of a little bit more deep into that return phase. We're into the place where we can begin harvesting energy. So what we need to do, if you think about our end product, pyruvate, pyruvate has no phosphates. So the phosphate that's present on each one of these glyceraldehyde 3-phosphate molecules, the fate of that is ultimately going to be in the form of ATP, or it's going to be added to make an ATP molecule. So this is a simple model of everything that's going on. For example, right here, we're going to make NADH. This is nicotinamide adenine dinucleotide. And anytime you see something go from positive to, and I'm going to ask you to add to the chat, NAD is positive. What's the charge on NADH? And that's not a trick question, but instead it's, yes, it's 0. There's no charge. Okay, so we've gone from something positive to neutral. So what has happened to that NAD plus to make it NADH? What has been added to it? I mean, the letter H, obviously, and a hydrogen, but it gained an electron. You're absolutely right. So when something gains an electron, what's that also known as? It got reduced. You're absolutely right. So I always like to highlight this because what that means is that NADH can be oxidized. And this is one of the challenging parts of biochemistry. So NADH can be oxidized. In addition to that, when you think back to like Gen Chem 1 and you think about oxidation and reduction, you have, oil rig and everything like that. But let's think about a very easily oxidized species. So Na, sodium. Sodium very easily, does that get oxidized or reduced? Would everyone agree that sodium, elemental sodium, gets oxidized very easily? Perfect. Okay. Now, what happens? Let's say that I got a piece of pure sodium or pure potassium, and I dropped it into a bucket of water. What's going to happen to it? It's obviously going to get oxidized, but visually, what am I going to see? I'm going to see smoke. I'm going to see fire. I'm going to see something dramatic. I'm going to see this energy that's being actively released. I like to bring that up because effectively, by making this molecule, this NADH, we've made a substance that, under the right conditions, can release a huge amount of energy. That's what that can do. So that's why we talk about, and that's why we value oxidation and reduction related reactions in glycolysis. So we're making NADH right here. So this is a high energy compound. Then we're going to make another high energy compound in the form of ATP. And that's where we're going to be basically getting back our high energy compounds. And then we'll get another pair of high energy compounds. So from glycolysis, really what we get are two NADH, because remember, this, as soon as we get to glyceraldehyde 3-phosphate, everything that we do happens 2x. So we get two NADH. Then we get two ATP. Then we're back down here and we're making ATP. So NADH and ATP are your high energy compounds that you get from glycolysis. So it's not simply, oh, I got a lot of ATP. That's the important part of glycolysis. Instead, you have this kind of sleeping giant of NADH that you're getting from glycolysis. Now, the steps that are involved in this. Okay, so remember, this is taking place 2x. So we've got glyceraldehyde 3-phosphate, Ga3P. So our phosphate is found on carbon number 3, 2, 1. Then what we're going to do is we're going to reduce NAD+, and by virtue of that, we're going to be oxidizing glyceraldehyde 3-phosphate. And in the process, what we're going to be doing also is we're going to add a phosphate onto glyceraldehyde 3-phosphate, where we make 1,3-phosphoglycolate. So the enzyme that does this is known as glyceraldehyde 3-phosphate, and this DH, that stands for, does anyone want to guess? Maybe not guess, but does anyone know? Okay, I like that guess. Dihydride, that's a pretty good guess there. Dihydroxy, you guys are super close. This is a dehydrogenase. That term dehydrogenase is pretty synonymous with enzymes that are involved in oxidation and reduction. So anytime I say, hey, we're working with this enzyme that's a dehydrogenase, I want you to think, okay, I hear dehydrogenase, that is going to catalyze a reaction where there's oxidation and reduction. Now, after we've produced this 1,3-bisphosphoglycolate, I'm going to erase dehydrogenase now. We've got a phosphate on carbon number 1. We've got a phosphate on carbon number 2. Great. Now what we're going to do is, wait a minute, wait, what? That's bonkers. Where did this phosphate come from? This phosphate that we just added, notice it's kind of right here. It's almost like, hey, yeah, it's just there. It's not a part of ATP. It's not a part of ADP. This is going to be presented as PI, or inorganic phosphate. So that inorganic phosphate can be added directly onto one glyceraldehyde 3-phosphate to make our 1,3-bisphosphoglycolate. That 1,3-bisphosphoglycolate is a molecule with 2 phosphates. We're going to use phosphoglycerate kinase to remove this phosphate, add it onto ADP, and make ATP. So we are going to you could almost say that we're putting the phosphate group on just to take it off immediately. That inorganic phosphate gets put on to make 1,3-bisphosphoglycolate. It's almost like that's the priming, and then we just pop it off to make 3-phosphoglyceraldehyde. So this is 3-phosphoglyceraldehyde. Okay, so or no, sorry about that, glycerate. I got mixed up. I apologize for that. It's glycerate. And the reason that I know that it's glycerate is because we've taken where there was an aldehyde and we replaced it with this functional group. What functional group is that? I'll give you a hint. It starts with oh, perfect. Great job. It's a carboxylic acid. So we've added that carboxylic acid on there in place of that aldehyde. All right. So what we've done is we've added an inorganic phosphate. We've made NADH. We've made ATP. And then we've made a carboxylic acid functional group. Now, with that in mind, let's think about our ATP overall up until now. So from glucose to now, let's balance our books. How many net ATP are we at right now? How many have we invested and how many have we gotten back? What do the books say right now? Net neutral, perfect. At this point in time, we're at exactly, we invested 2 and now we've gotten back 2. So if we wanted to, we could just quit this business venture and move along and just be like, well, that happened, but we can do more than that. In addition to that, a little bit of a looking ahead, we have this NADH. That's a high energy compound. And that's not just high energy in just some abstract way. Your body and eukaryotes use that NADH to extract a bunch more energy and produce a lot of ATP. Now, essentially, we're now right here, where we've gotten back ATP, we've gotten 2 NADH. Great, we're in a good place right now. So now if we make any more ATP, we're going to be more positive. So we've got 3-phosphoglycerate, the molecule that we just produced, where we've got a phosphate on carbon number 3, we've got our carboxylic acid on carbon number 1, and we're going to do an isomerization. But this isomerase, or this rearrangement, this isomerization is going to be catalyzed by an enzyme known as phosphoglycerate mutase, or PGM. Essentially, all that we're doing is we're taking our phosphate group from carbon number 3 and we're moving it to carbon number 2. That's all that we're doing. Now, there's a little bit more to this mechanism and some terminology related to this mechanism as to why it's a mutase as opposed to an isomerase. But that's what we're doing. We're taking our phosphate from carbon 3 and putting it on carbon 2. Now, with that new molecule, this 2-phosphoglycerate, and actually, let's go ahead and take a pause right here. Does this get us any more NADH or ATP? If we stopped right here. Nope, we're still at 0. Okay. But this does set the stage so that we can, because we've got this phosphate molecule stuck onto our 3-carbon sugar. That 2-phosphoglycerate, what we're going to do is we're going to do a dehydration reaction or condensation reaction. We're going to remove this hydrogen from this hydroxide. We're going to produce water. And this is going to be done by the enzyme known as enolase. It's going to take 2-phosphoglycerate, our carboxylic acid containing phosphorylated 3-carbon molecule, and we're going to remove that H2O, and we're going to make phosphoenol pyruvate. That puts our phosphate on carbon number 2. That phosphoenol pyruvate is going to be essential because with that phosphate on carbon number 2, we're going to remove that and put it onto ADP in order to make ATP. So the enzyme that catalyzes this reaction is pyruvate kinase. This is an irreversible reaction. This takes phosphoenol pyruvate and makes ATP and pyruvate. Okay, so one thing that I suggest that so this is where we're done. So what's our net ATP? 2. We've got positive 2 ATP. I had a question that was, is this ADP from a previous step, or was it just in the body and the cell? It's just an ADP that's around because this is taking place in the cytosol. This process is taking place in the cytosol, and there's tons of other processes that will generate ADP. So don't think about this necessarily as, oh, it came from a previous step. No, there's an excess of ADP available. So yeah. Okay. Now, with that in mind, there's a bit of this, and to look at the mechanism, sorry, I'm going to look at the mechanism, then I'm going to bring it back and talk about different ways to analyze this. Okay, so this phosphoenol pyruvate, here is phosphoenol pyruvate. This phosphoenol pyruvate is where we're going to release a phosphate in order to make ATP. That release of ATP is going to make pyruvate. So essentially, that's what I want you to know about this step. I want you to know about, okay, phosphoenol pyruvate is donating a phosphate group in order to make pyruvate and to make ATP. This is happening 2x, so we have 2 ATP. Now, with that to say, and with that in mind, I want to look at this figure again. Actually, I'm going to blow that up. Let's see, sharing. Okay, good. I want to bring this one up because there's a couple of different ways that I think are important to look at this. And there are a couple of ways that I think that are helpful for learning what's taking place. If you were to look at going from here to here, so your investment phase, what I think is helpful from like a conceptual standpoint, because I want you to know the details, and I'm going to ask you about the details, the structures, the names, and to be able to identify the structures and be able to identify the molecules by their full names. I want you to know how to do those things, and I want you to know those things. This is our investment. A quick summary of the investment is you have an aldose and you phosphorylate it. 2 times. And your output is a 2x phosphorylated ketose. Okay. Now, How do you go from an aldose to a ketose? You have to have an isomerization. Then what you need is in order to like fully get into the remainder of the pathway, you need two singly phosphorylated 1,X phos aldoses. So you need to have an aldose that's been phosphorylated 2 times. I'm sorry, let me rephrase that. You need to have 2 aldoses that have been phosphorylated 1 time. You need to have glyceraldehyde 3-phosphate. Okay. You're going to then take those 2 aldoses and you're going to phosphorylate them. Phosphorylate with PI, inorganic phosphate. Then whenever you add that inorganic phosphate, you're going to use that to make ATP, and you're going to make or replace aldehyde, your aldehyde with I'm going to say COO minus, your carboxylic acid. Then you rearrange to make, you rearrange the molecule, and then you remove water. And once you've removed water, then you can remove phosphate to make ATP. Now, I like to look at this pathway using all this sort of terminology, because what this is really demonstrating and stressing is the kind of important actions that are taking place. This simplifies this pathway because what it's really leaning on is bringing back terminology that you've seen before. And it's doubling down on terms like aldoses and ketoses. Are those important? Absolutely. What people have a tendency to do, and I want to caution you kind of against this, is people have a tendency to take this figure and, commit part of it to memory. And then they commit it to memory, but then the problem that they run into is similar to the problem that I was describing earlier with, hey, draw glyceraldehyde 3-phosphate, now draw glyceraldehyde. And they're like, uh-oh, I don't know. You've changed one simple part of this, but now I'm completely at a loss. So I want to caution you against that, because that can lead to unintended consequences, unintended negative consequences, where you think you know something, but then all of a sudden you don't. Okay. Now, to sum it up, that's what I would recommend doing. I would recommend trying to give a brief description about what's happening and use as much terminology as you can from what you've previously learned and what we've talked about in this class. Now, one molecule that I think is very important to know the structure of that people often neglect is this one right down here, pyruvate. Because what happens is people will commit the first 3 structures to memory, first 4, maybe even the first 5, and then they get like a fatigue, because in here what's happening is you're like, oh, I'm just rearranging these. I'm taking this phosphate from here and I'm putting it here. It's all just kind of a mess anyway. It's okay. I don't need to worry about that. That just sort of sets in and it really presents a problem. My strategy for learning this, whenever I took a metabolism class in graduate school, was I started at each end. I learned glucose, I learned pyruvate structures, and then worked inwards. And that was helpful for me, because then I was like, well, how did I get from here to here? Okay, how did I get from here to here? And it became much more clear as I was looking at, an enzyme like glyceraldehyde 3-phosphate dehydrogenase. And so at any rate, I'm going to go ahead and stop my recording. There's a question, what day is the exam on?